So it is our great pleasure to have invited Professor John Dickerson from University of Maryland's computer science here. He is also a chief scientist of Author AI, and he had obtained his PhD in computer science from Carnegie Mellon University. Has received various awards such as NSF Career Awards, IEEE Intelligent Systems AI's 10 to Watch Global Faculty Research Award, and various rewards. And so it is indeed our great pleasure to have invited him here. And John, you have the floor.
Fantastic. Thank you all for the invitation, and it's a real pleasure to give a virtual talk here. Today I'll be talking about some recent work that we've been pushing forward. This is very hot off the press's work in that like only one of the papers has actually appeared that I'll talk about today in a conference for NeurIPS, and the others are sort of under submission. So it's very hot off the presses work using deep learning to design auctions. And I do want to shout out to my lab and colleagues here. You know, as with all things in academia, the work is a collaborative effort. A lot of this has been led by my PhD student, Michael Curry. And just to hit the last name here, Anthony Ostuni, he's a graduating undergrad who just accepted actually UCSD's CSE PhD offer. So he'll be starting with you all in a few months. Cool, so I'll kick this off with a quick motivational quote. Market design is a kind of economic engineering, utilizing laboratory research, game theory, algorithms, simulation, and more. Its challenges inspire us to rethink long-standing fundamentals of economic theory. And this is a quote from an address given by Paul Milgram when he won an award back around 2008. And it's very motivational and sort of draws a strong connection between economics and computer science. And that's actually work that he's continued to draw to the point of actually winning the Nobel Prize in the last couple of months. So what is market design? And I'll design this roughly loosely for this talk. And you may have your own opinions on this, but I'll say at a high level, market design is partially based on mechanism design. Roughly speaking, this is the design of incentives toward a particular goal in a strategic setting with one or more agents. Okay. So what do I mean by design of incentives toward a particular goal in a strategic setting? So design of incentives, this could be things like pricing and allocation rules and auctions, right? You go on eBay and you bid for something, and then you win or you don't win an item, and then you're charged some money or you aren't. Or a lot of my work in my lab focuses on what are called matching markets. That's not the topic of today's talk, but I've done a lot of work in organ allocation, blood donation, labor markets, and so on. These are forms of matching markets where you're interested in joining agents to each other or to contracts or other transactions. Toward a particular goal, well, we're optimizers. We like to maximize global welfare. We have to maximize social welfare. Maybe subject to some form of fairness, right? And this comes with all the caveats of defining forms of fairness that you would expect. Or in the case of this talk, we're interested in maximizing revenue for a clearinghouse, let's say. So I'm an auctioneer, I'm eBay, and I want to maximize revenue. And strategic setting, the third of these phrases I've color-coded. Well, a strategic setting basically means that we have agents and their strategies are based on what they think other agents are going to do, which are based on what they think other agents are going to do, which are based on other, and ... all the way down. Okay, so there's strategic thinking, strategic revelation of information toward a system to benefit one's own self. Well, I'll today focus on a specific type of mechanism design called auction design. And again, this is for the sake of this talk, I'll define it as an auction mechanism being run by a central coordinator. Sometimes I use the word principal or clearinghouse, who asks agents to report their preferences, in this case directly. And then I'm going to aggregate them as the clearinghouse or the principal or the coordinator. I'll aggregate them in some way and I'll decide who gets what. And this could be probabilistic, and then maybe I'll charge you some money. Agents, bidders, for example, are going to have private information about their own personal preferences. Okay. To put this into econ lingo, this is going to be their private type theta, and that's going to be drawn from some space of private types. For example, I have a water bottle right here, and I secretly value it at 0.6. You don't know that, but you do know that I drew this private type 0.6 from some distribution, let's say uniform 0, 1. We can look at this in pictures as well. I think this is more convenient for this talk. And I do want to say, this can be a very chatty talk. Feel free to ask questions in chat or unmute yourselves if that is possible, given the settings on Zoom. Happy to talk in general. This is what the auction model will look like. This is how an auction will work for the context of this talk. And this is a traditional model for auction theory. Okay, so we're going to have a publicly known valuation distribution for each agent. Okay, I'll have n agents indexed by I, and I'll have k items indexed by j. I could have one agent and one item, for example. I'll know the distribution from which the agents draw their valuations for the items. I don't know the actual valuations that they draw. Agents know their actual valuations, their private valuations, and they can strategically reveal those valuations in the form of a bid to a central system. That central system will run a function that aggregates all these bids, B1, B2, BI, up to BN, and then does two things. Allocates some items and charges players based on that allocation and their bid and the other players' bids. Okay. So here we have an allocation vector AI, which lives in the space of k goods. And this could be zeros and ones, or this could be values between 0 and 1 with probability distribution constraints and so on. And then we have a price, and that's a real value. Okay. Following this, agents receive some utility based on their private valuations, what they get, and what they're charged. Okay. So if I value my water bottle at 0.6 and I get it and I'm charged 0.4, in a very simple model, I might get utility of 0.2, 0.6 minus 0.4. Okay. Cool. So that's the model. So we'll make some assumptions. And these are common assumptions. It's a common model. Agents are going to be rational utility maximizers. Okay. This is a very strong sense of rationality. So they're going to be, they care about how well they do. Right? So that utility that they receive as a function of their private type and what they get and what they're charged, that's what they care about. They want to maximize that. And they're going to play some form of equilibrium. And it's known that designing mechanisms in general that have sort of good equilibrium behavior is hard to do. Okay. And good here is going to mean that we implement some function f, for example, social welfare maximization or revenue maximization under strategic behavior. Okay, so here's a common plot where if we didn't have strategic revelation of agents' private types, then, well, this is just a traditional computer science problem where we take as input some input data, and then we run a function and we spit out an outcome that maximizes revenue or maximizes social welfare or whatever. Well, agents are doing strategic revelation. So what we want to do is we want to design a system, a mechanism, an auction, which is going to incentivize them to truthfully reveal their private information to me as a central auctioneer in equilibrium. And I want that to implement this social welfare function, right? That's what I want. And this is a no and hard problem in mechanism design in general, as well as in auction design as well. So some goals we might have while designing these auctions, and these are phrases from sort of the econ world, we might want individual rationality, or IR. And in the vernacular, this just means that anyone who plays truthfully reveals their private type to the central system, won't leave the system strictly worse off than they would have by staying home. So put another way, you're not going to get negative utility by behaving well in my auction. Okay, so I'll call an auction or a mechanism individually rational if that holds. And we might want a second very strong condition, something called dominant strategies incentive compatibility, or strategy proofness, you may have heard it called. It's a little bit easier to say than DSIC. It's always optimal to bid your true valuation, no matter what others do. That's a very strong condition. Okay, so I don't have to look around and think about what others are going to do. It's always going to be weakly better for me to be truthful than it would be for me to lie to the central system. And in the context of what we'll talk about today, I can measure this in a form of what's called regret. And so I'll incur regret if I bid truthfully and get some utility, and then look around and think, well, if I had bid differently, could I have done better? And if I can do better, well, pick the best bid that I could have done that isn't truthful bidding. Pick the best one, the one that maximizes that delta, and that's my regret. Okay, so if regret is 0, then I'm not better off by lying, and if regret is positive, then I should have lied if I'm a selfish utility maximizer, which of course I am. And we're interested in revenue maximization. So we want the sum of the prices that we charge the agents indexed by I to be as large as possible. Okay, I want to extract payments from my agents. So any questions so far? Actually, not sure how I can receive questions. Maybe that's a silly answer or a question to ask. Okay, I'll assume that I can't. So an optimal auction is going to be incentive compatible. Today we'll talk about dominant strategies incentive compatible, but there are other forms of incentive compatibility. It's going to be incentive compatible. It's going to incentivize truth telling, and it's going to be revenue maximizing. It's a specific class of auctions. And analytic results in this space are incredibly hard to create, notoriously hard to create. Sort of the big paper that kicked a lot of this off was work by Myerson in 1981, who resolved this for the case of one item. Okay, one item. So you can imagine auctions that have more than one item, and they're not resolved in this paper. And there's been some progress since then, but even 2 items and 2 bidders, so 2 items, 2 agents, this is not fully resolved. Okay, so if I ask you how to design an incentive compatible revenue maximizing, i.e. optimal auction for, say, 3 items and 3 bidders, then not known. And there's been a ton of really elegant, beautiful, principled work in this space coming from a number of different fields, econ, CS, math, ORMs, stats, and so on, in the last few decades. They typically focus on a weaker notion of incentive compatibility. And again, we're sort of at this 2 item, 2 bidder case still. Okay. Cool. So analytical results, I'm really going to harp on this because often people will say, well, why are we using like a complicated deep net to design these sorts of things? Why can't we just think really hard? Well, it turns out thinking really hard isn't quite enough yet. Analytic results are very tough to create. So here are, and I'm not going to do justice to the full space of a few decades of work here, but here are a couple nice results in the dominant strategy setting for, say, 2 items and 1 bidder with what are called additive valuations. So we'll talk about different demand models. Additive valuations means if I have 2 items, I value item 1 at V1, I value item 2 at V2. If I give you both the items, then you value that bundle of items at the sum of the individual items valuations. Okay, so that's additive valuations. There's no, say, substitutes going on here. Okay, so 2 items, 1 bidder, there's good stuff known. 2 items with unit demand bidders. Okay, so unit demand is basically saying if I give you some large number of items, you're just going to get the utility based on the one you value the most. So you only really want 1 item, but not more. Okay, so this is sort of a quick overview of where we are from a theory point of view. Something to keep in mind is we're looking at revenue maximization. There's a whole extra lecture here on social welfare maximization with very beautiful results where I'll use words like second price or BCG. We're talking about revenue maximization, and revenue maximization has some interesting bits. One is that not allocating an item is okay. This is generally not going to be okay if you're doing social welfare maximization. I mean, unless the agents hate the item and don't want it. But in general, if you have a bunch of items and the agents have some value for them, you're going to want to give them to somebody. In revenue maximization, sometimes it's okay not to allocate an item. And you can use that as a sort of lever that says, well, sometimes I'm not going to allocate that item, in which case I, as the central auctioneer, get 0 profit, right? Get 0 revenue from this, right? I can't charge you money for not giving you something, or else this is not going to be individually rational. But if I have that stick, if I can use that as a threat, then sometimes I can push you up above where you would be otherwise, okay, in terms of money. Cool. So just something to keep in mind. Great. So what if there are more than 2 items and more than 2 bidders? Well, we're not totally out of luck. So one is, as in all things, you can be informed by theoretical analyses of smaller general systems, right? So we do have these nice, elegant theoretical analyses of smaller auction systems. If you go to like your Facebooks or your Amazons or your Googles of the world, there are large groups of people who have intimate knowledge of these theoretical results who use them to help design these more complicated real-world auction systems. So theory really does help practice here. You can design approximately optimal mechanisms. Okay, so I can relax maybe a form of incentive compatibility, or I can relax my goal of revenue maximization, and I can maybe get a little more progress there. And you can use automated mechanism design. Okay. And what is automated mechanism design? Well, we're going to be most motivated by this. And the general pitch here is that we want to we don't want to look at the general case. We're going to take as input a particular problem instance, and then we're going to cater fit an auction for that specific problem instance. Okay, so for k is equal to 3 and n is equal to 2, and for valuation distributions that look exactly like this, I'll use some mathematics to design an auction for that particular case. This is automated mechanism design. So we're gonna focus on that here. And the idea sort of sprung up with the genesis of the Econ CS community in the early 2000s. A lot of the earlier work runs into scalability issues, and so it becomes less practical. We're going to try and relax that as well. Okay, and how are we going to relax that? We'll hop back to our auction model. Right? It's hard. I've motivated that it's hard. So you're like, never going to get this to work. Well, one thing we can do as computer scientists is we can just replace our function that allocates things and prices things with a neural network, and then let the GPU solve everything. So if you're going to remember one thing from this talk, remember this slide. It's replacing that function that aggregates bids and allocates goods to agents and allocates payments, or extracts payments from agents. I'm going to replace that with a neural network. So this is a type of what is called differentiable economics. It's a phrase I love, and it's only been around for a few years. So I'll bring it up here just so it starts to catch on. It's the econ version of what's called differentiable programming, right? So that's a term coined by Jan LeCun, which basically says, hey, I can build software by jamming together building blocks that I can backprop through. Okay. So deep learning would be a specific type, for example, of differentiable programming. I can then use this as a building block. I can connect things together, and then I can sort of use gradient-based optimization to solve a problem. So differentiable economics was coined in the same spirit by David Parks, who's a EECS at Harvard. He's an econ CS guy, who says, we're interested in just combining these same basic building blocks to create mechanisms, auctions, matching mechanisms, right, that are differentiable. And so I can learn a good auction just using, gradient-based optimization methods. Okay. Cool. So the first big work in this space introduced RegretNet, along with something called RocherNet, which I won't go over in this talk, but RegretNet and some other similar networks. And their focus was on dominant strategies, incentive compatibility, and revenue maximization. So optimal auctions, where we have this strategy proofness concern. Again, we're going to replace that function f that aggregates bids with a deep neural network or a pair of networks, depending on how you look at it. Okay. We want to maximize revenue, and we want incentive properties that are good. So how do we maximize revenue? Well, we can include a revenue term in the loss function during training. Great. How do we deal with incentives? Well, we can include them in the loss function as well if we'd like to, right? Like this is a constraint on the system, and there are a variety of ways of training deep networks with constraints, right? I can, whisper something about Lagrange multipliers, or I can actually use full constraint optimization or whatever. Basically, I'm going to compute strategic inputs in the context of that regret term that I discussed earlier, and we'll discuss again on the subsequent slides. And then I can just, during training, I can use gradient-based methods to reduce violation of the strategy proofness constraint. Okay. So I'm gonna penalize low revenue, and I'm going to penalize networks that are manipulable, that violate strategy proofness. So regret, right, is this max over bids. I have a bunch of different bids that I, as an individual agent, could consider giving to a central mechanism, right? I draw my private type, my 0.6 for a water bottle, and I can bid anywhere between 0 and 1, right? I want to truthfully bid my private type, right? I want to truthfully bid 0.6 because that would be, well, that's truthful. But if I think about every single other bid and then pick the one that maximizes my utility, and that's different than what my utility would be if I were truth telling, then I have positive regret, right? So solving that maximization problem is actually very tricky because determining the utility that I'll receive from, say, strategically revealing my private type is hard, right? Because that utility is a function of this neural network. And those are really weird looking functions, right? So it's hard to solve this maximization problem partway through the talk, I'll talk about one way to exactly solve it. This is a NeurIPS paper we had a few months ago. It's hard to solve this exactly. And so one thing you can do is just, just estimate it. I can actually just do gradient ascent on this utility and then come to an empiric estimate as to what regret is. And so this is what RegretNet did. The inputs are relatively small. The networks are relatively small in the grand scheme of deep learning, right? You just have a few hidden layers here. The inputs are relatively small. You're drawing from number of agents times number of items, basically valuations, and putting those in as bids. So you can do a lot of this to get a reasonable estimate, but it's going to be an underestimate of the regret. And then this is easily implemented, and you can just rely on sort of auto-grad to get around it. Okay, so we're going to initially estimate this regret. Okay. So what does training look like? Well, our data set is just going to be a large number of random samples from the public valuation distributions. Okay, so with one item, if I'm drawing from uniform 0, 1, it's just going to be a sample from uniform 0, 1. And then, well, because our end goal is a strategy-proof, i.e. truth-telling basically mechanism, I only have to assume that agents are going to bid truthfully. So I don't need a behavioral model of what my agents are going to do here. I can just assume that they're going to bid truthfully from the get-go and then train my way to a network where that's actually the right strategy for them to take. Okay. And my goal would be to ensure 0 regret with high revenue. So we can look at what our loss function might look like, right? Our loss function is going to have basically 2 terms. I'm going to minimize my loss, just like I normally do in machine learning. I'm going to get minimize, basically penalize low profit, right? Minimize negative revenue. And I'm going to penalize high regret. So if regret goes down to 0, then I'll get no penalty for regret. And as I jack up the sum of my payments, I'm going to lower my loss function, which is a very good thing when I'm minimizing. That's the whole thing. And then I just train it just like I would normally using SGG, just like any neural network. These are not complicated. Structurally, these aren't complicated neural networks. Cool. So this paper successfully recovers a number of known results in the auction design space. And it's maybe not super important for this talk, but here are some pictures of, let's just focus on this is pictures of 5 2-item, 1-bidder cases where the optimal auction is known. The analytic optimal auction is known. Okay, so on the x-axis, we're showing the valuation for one item, and on the y-axis, we're showing the valuation for another item. And then this little black line here is showing the dividing line between I allocate a bundle of goods or I don't. Okay, so here is with probability 1, I allocate item 1 to a user. Here's with probability 1, I allocate item 2 to a user, and 0 otherwise. Okay, so this dotted line is the analytic optimal, and then the heat map is reading out the values from the neural network. And you can see that they align very well. Again, it's not important exactly what leads to these figures. Just know that they look like the analytic optimum. And in many cases, right, it's not known what the optimal auction is. And so in that work, they compare against a number of strong baselines and show that this works pretty well as well. So that's promising. I want to talk about in today's lecture, and again, this is a fairly new talk, actually a very new talk, and it's very new work. I want to talk about some tweaks on this, right? So I want to kind of sell the general approach of differentiable economics, and I want to sort of show what you can do with it. Right? So I'll start with a quick warm up where we can start tacking on additional terms to the objective, to the loss function of our network during training, to do things like encode forms of fairness into the auction design problem. Okay. And then we'll move into some work where we talk about providing the first certifiable learned auction networks. Okay, so we have an underestimate of this regret. How bad is that, right? And so we lean on some techniques from the adversarial machine learning community to design certificates for trained networks. And I'll close out with some very hot off the presses. In fact, it's not even on archive yet, so feel free to reach out to me to talk about this, where we are able to incorporate new demand types into the training process by way of tacking on a differentiable matching. Post-process isn't the right word, but it's a different building block toward the end of the training process, where we rely on basically Sinkhorn's algorithm to solve a discrete optimal transport problem. And this actually enables some new types of inputs to be used that weren't previously usable. So I'll start with a warm-up. It's known that online advertising has issues with forms of discrimination for a variety of definitions of discrimination. So here are some famous papers in this space. So some work from Anupam Datta's lab at CMU showed in around 2015 that Google would display job listings, for example, of higher income to men and lower income job listings to women, holding their feature vectors constant otherwise. Okay. Facebook, for example, would send ads discriminating based on gender, regardless of advertiser preferences, right? I'm not picking on these particular tech firms here. This is just sort of a ubiquitous behavior that was observed in a variety of different papers. Okay. And more generally, I would recommend this paper by Shuchichawa et al., which appeared at what was FatStar, what is now Fact last year, basically saying that online ads have been shown to discriminate on race, drug use, parental status, and so on. There are a lot of good citations in this paper that will sort of lead you on down a rabbit hole of discrimination in advertising. Okay. And if we put on our optimist hat, we can say this is unintentional, but it's going to be inevitable without actually considering it in say the optimization problem. And so for this warm-up, we're going to have a new goal, which is going to be to prevent unfair, for some definition of unfair, allocations between users. Users are going to be items, so eyeballs, and bidders are going to be the advertisers. And I do want to be explicit with my caveat here about the use of the word unfair here, right? So ensuring unfairness or proving unfairness, or proving fairness, right, in machine learning systems it's kind of a vacuous or meaningless statement in the sense that these are systems that are part of a larger social context, and so the decision of using a particular definition of fairness in a quantitative sense, or considering that at all in the training process, is one that obviously John should not be making, but stakeholders should be making. And so this is a proof of concept to show exactly what one can do. Cool. So our setting here, same setting, is that advertisers are going to be the bidders, and they're going to bid on users, the items, J, right? So we have advertisers indexed by I, we have the items indexed by J, and we're going to have an auctioneer, and they're going to allocate users these items depending on the bids. Okay. And there are a bunch of other qualities that might impact that allocation, such as relevancy of an advertisement to eyeballs. This is hugely important, for those who have worked in advertising before. The FANGs of the world really care that you're not being shown, low resolution, terrible advertisements, right? The creative has to be high quality and so on. Okay. And for some definition of fairness, we would like to prevent or highly discourage allocations that induce that unfairness. Okay. So we'll take a common definition, initially proposed by, I believe, Cynthia Dwork, and then more recently used specifically in the auction setting in this work by Shuchichawa, called total variation fairness. Okay. Here, users are going to be who are similar, okay, by some distance metric between users, should be allocated advertisements similarly. Okay. So the more similar users are, the smaller their distance d is. Right? So if we have identical users, d will be 0. And we're going to try to treat similar users similarly, right? Similar items similarly. And we can encode this in a specific way, right? So we have items, users, j and j prime. Pick a pair of users, j and j prime. And I can look at the allocation of these users, j and j prime, to a specific bidder I, right? So I look at that element in the allocation vector. So Zij is going to be the allocation of j to I, and Zij prime is going to be the allocation of j prime to I. I can look at the difference between the two, sum it all up. That'll give me a total variation. And if that's less than or equal to some function of this distance, then I'll say it's fair. So as distance grows and grows, as the users become less and less similar, then I'm given more sort of wiggle room when it comes to treating the two differently in my allocation vectors. And as I push the users together, then I'm given less and less sort of wiggle room in my ability to allocate differentiated. Okay. And this is just an example. Again, the same caveats hold, but it's one that I could see, being used or useful at least in the advertising setting. And this has been motivated by others. Cool. So again, I said this is a warm-up, and it's a warm-up for the particular reason that, well, all we're doing is tacking on a term to the loss function, right? So here's the RegretNet style loss, where we're again penalizing low revenue and we're penalizing high regret. I can define this total variation unfairness, right, as just summing over all the different users and then asking, well, in a pairwise fashion, how many of these unfair pairs are you a part of? And then adding them up. Okay. So ideally, you would be part of 0, and I would get 0 penalty for this. But as you are part of more and more of them, then I can jack up that penalty. Okay. And that'll be weighted by how unfair that pair JJ prime is going to be. And then our loss function is just going to add that on. Okay. Network stays the same. Training stays the same. Everything else stays the same. Okay. And some sample results. This recovers the kind of sort of results you would expect to see. Okay, so here's another sort of known optimal auction. All right, so here we have, again, the 2 items, 1 bidder. Here's a probability of allocating item 1, the probability of allocating item 2. The dotted lines are the known optimal auction. And the valuations are on the X and Y axis and so on. This is for revenue maximization. Using this proportionate framework, we're able to recover this exactly and then increase this penalty for unfairness until it dominates the loss term entirely. Okay, so if we look at these heat maps, just focus maybe on the first row here for the item 1 allocation. If we have effectively no fairness penalty, then we get the optimal auction. So this is identical to the heat maps you would find in other work here. But then as we increase this unfairness penalty, the sort of smoothing out that you would expect comes into play. Okay. So this is nice. It's nice because it just allows us to incorporate a specific form of fairness into this auction process. Okay. I see a hand up, but I'm not sure if I have permission to unmute you. Oh, Lily, yeah, if you can unmute yourself, feel free to ask a question.
Yeah, hi, John. So I'm curious about how do you define the similarity between users?
Yeah, so that's a function that's just given to us. So yeah, so
right.
I mean, you might have feature vectors associated with the items or the users, and then you can just create a distance function between the two.
So in this case, how do you define in your example? Is that something you already show? Sorry, I might be missing something.
Like the actual function for
yeah, yeah. What is the distance you consider here? You are considering here.
That is a good question. Oh, I see. Okay. Actually, so this D at the top here, yeah. Okay, so I've picked out the right figure here. This D at the top here is actually showing you the distance between the 2 items. Okay, so here I'm not jacking up a penalty here. I'm actually just increasing the distance, or actually decreasing it as I move from left to right, the distance between the 2 items. So we have exactly 2 items here. We have item 1, we have item 2. And this is what this would look like if the distance between the 2 items were very high. Okay, so I've normalized this to between 0 and 1. So 1 is very high. So basically, the fairness penalty will not come into play, because any allocation, right? If I have 0 allocation for item 1 and I have 1 allocation for item 2, then the distance between these is going to be 1 minus 0 or 1, which is always going to be less than or equal to the distance between the 2 items, which is 1. So here, the fairness constraint would never come into play. As I scoot the items closer together, then I need to treat them more and more similarly. In fact, as I scoot them on top of each other, which would be the furthest right here, D is equal to 0. They're the same item. I need to treat them exactly the same. And that's exactly what you see here, where I'm smoothing out either I give both items or I don't give either item.
Yeah, so I'm a little bit confused here. So is the item here means the user?
Yes. Yeah. So we have bidders, advertisers bidding on eyeballs. Yeah. It's a bit of a, I mean, this is not how online advertising actually works, or exchanges and, data is flowing all over the place, but it's a stylized model.
I see. Thank you.
Yeah, great question. Okay, so this is one way. It's amenable to the sort of knob turning, right? So I did a little cheat mode there for that last image where we're scooting the items together, right? So I'm playing around with the distance between the 2 items, but you can also imagine increasing or decreasing the penalty impacting your loss term based on that fairness as well. Okay. there are some tricky bits to this, right? So measuring expected unfairness can't be done directly, and we're going to have to estimate this. So we have a generalization bound in the paper that is on archive for this. It sort of follows directly from previous generalization bounds as well. And this model, of course, is a bit stylized. But I like to start with this in a talk like this because it really just shows sort of the flexibility of these models, right? Like it would be very difficult, I believe, to say here's an optimal auction that will work for a large variety of definitions of, for example, fairness, or I can do like diversity of items, for example, knowing like a recommender system. This will work for that, which is nice. Cool. So now we'll hop into something maybe a little bit more, I don't know, like mathy. We'll talk about certifying these trained networks. Okay, so this will apply to any of these sort of trained networks. And there are some limitations to RegretNet, proportionNet, and family. So the RegretNet family is concerned with minimizing regret, right? And it's going to use this gradient-based approximation to estimate regret, right? And this is great for training. It's very fast, but it may underestimate. In fact, it does, and we'll show it does underestimate regret. And I do want to do a quick shout out to a couple of related works here. So like I mentioned, this paper actually presents something called RegretNet, which doesn't have this gradient-based approximation for regret. That's only for the single bidder case. So we're looking at more than one bidder. There's a related paper by Shen et al. In 2019. So these are folks from I believe Tsinghua and Google and from Renmin University who have a different approach, but again, just for one bidder. So there's, we're looking at a different setting than that. Okay. And then there's been some nice work coming out of some groups at Princeton. One of these is appearing at iClear 21, which actually replaces this approximation step with a neural network. And we played around with that a little bit in my lab as well, and that seems to work pretty nicely as well. But that would actually have the same issues with underestimating regret. So quick aside. Cool. So we want to compute regret exactly, right? If I have an exact computation of regret, then I can fight manipulation. Well, it's hard, right? Neural networks are very weird, but we can use techniques from the robustness and machine learning literature to encode neural networks as, say, an integer linear program and then solve for regret exactly. And that's indeed what we're going to do. Okay. Cool. So modern neural networks, blanket statements, they always go over well in talks where it's hard for people to actually ask questions. So modern neural networks are mostly piecewise linear. They're mostly, stacks of raw use. And this is nice because then I can throw things into an ILP. It is possible to embed these into IPs using, if you're an ILP person, it's kind of intuitive. If you're not an ILP person, there's something called a big M formulation, which allows you to basically encode piecewise linearity, or you can think of it as encoding an if statement in a linear way into an integer linear program. And you can encode a ReLU neural network, ReLU-based neural network into an ILP using these same functions. Cool. And then once I've done this, I can maximize over inputs, right? So for a particular draw from a valuation profile, I can then maximize over inputs and compute regret with respect to truthfully bidding. Okay, and I can just do that using integer programming. And there has been a lot of work in this space that we can just lean on here. Here we're using a relatively naive embedding of the neural network into an ILP, but there's a lot of really nice work on scalable methods for embedding much larger networks into ILPs that I would love to see as future work here. And if this is motivated in large part from the vision community for now, and increasingly from the NLP community, you'll often see pictures. This is like a standard picture for computer vision, where you're able to do a small perturbation to an input image of like a panda, and you can change it from being labeled as a panda into being labeled as something that isn't a panda. Okay, so there's a lot of work in this space that I'd be happy to talk about offline. For us, we're interested in computing the highest regret bid. Okay, so I can look at my truthful bid, and then I want to shade that bid a little bit to incur some regret. And there's some challenges here. One is that RegretNet, as with modern neural networks, uses basically a set of softmaxes to enforce allocation constraints, right? We have to have a feasible allocation of some finite number of items to some finite number of bidders. And to enforce that feasibility, right, these feasible probability distributions, I can't allocate more item than I have. I can't allocate, two of item one to somebody. So to enforce that, RegretNet style approaches, these differentiable economic style approaches, use a series of softmaxes and mins, and it's hard to fit that into an ILP, right? Because the softmax isn't L, right? It's not linear. So we can actually replace this if we'd like to with a sparse max. Okay, so I've shown here a softmax in blue and a sparse max in red, and roughly speaking, this is just kind of as a piecewise linear approximation to the softmax. Okay, and we can formulate this as an optimization problem and embed this into the ILP. Okay, so it's a little bit different, and in fact, we do drop a little revenue in our experiments for this, and this is still a bit of an open question. I mean, we're an academic lab, so we don't have Google level GPU access. So some of this could just be a training issue as well. Now, a second issue we run into is that RegretNet and ProportionNet and so on, they enforce individual rationality, this idea that I'm not going to leave an agent with less utility than she entered with. This individual rationality constraint exactly. If we were to encode this directly into an ILP, we would run into some issues with sort of quadratic constraints. Okay, and it's basically because this is a product of two disjoint variables. Okay, so if I were to encode this into an ILP, I basically have the statement: charge a payment if and only if you're allocated an item. Okay, I can't have the issue where I charge you a payment and I don't allocate you an item, because that would actually violate individual rationality, right? You get negative utility for that. These are both variables, though, right? I'm figuring out payments and I'm figuring out allocation, so I have to jam them together. This is a product of two variables, which results in a non-convex bilinear equality constraint. A couple of ways around this that we tried, and they both seem to work pretty well. So one is to eliminate it and just jam it up into the loss function, as one does as a machine learner, right? So you can encourage individual rationality just like you encourage incentive compatibility, just like you encourage revenue and so on. And this actually works pretty well. And the other way is you can just rely on the black magic that is known as these black box optimizers, basically, like Gurobi or Cplex and so on, to solve it for you. And so Gurobi 9.1 and later, just fortuitously as we were working on this, came out with ways to handle bilinear constraints. And so these are just special cases of non-convex quadratic constraints, and they can handle them, which is great. So both of these methods, we worked with both of them, and they both seem to work pretty well. Cool. So here are some experimental results. So here is a RegretNet, and I have all the code at the end of this talk, so I'm happy to share this. It's a PyTorch implementation. That's quite nice. Here are some results on a RegretNet. Okay, so this is pointwise. This is local certification. Here we're showing in blue. So okay, so just focus on one of these dots. Same two items, one bidder case. Here we're showing in blue a truthful bid. For example, for the draw 0.5, 0.2, this is a truthful bid. And then in red, we're showing the bid that you should have done, okay? The one that maximizes regret. Okay. And some interesting things pop out of this, and I'm only showing it for regret greater than some lower bound. Some interesting sort of qualitative results pop out of this. One is, well, it is indeed the case that if you train a RegretNet, for example, it underestimates regret. Okay, so these result in sort of manipulable final networks. And two is there's some interesting structure here, right? So this sort of like this line here seems to align with some of the heat maps we saw in previous slides. And this is again an open question. This is very recent work. I do think there's probably some interesting work to be done here as well. And in terms of solve time, we're able to solve beyond 2 by 2, which is I should have included that table here. In a reasonable amount of time. So this does increase, obviously this does increase some train time issues, but we're able to provide certificates on these RegretNets, which is kind of cool. Lily is raising her hand. Feel free to, yeah.
Yeah, sorry, I have another question. So I'm not familiar with the RegretNet. Can you tell us a little bit about what is the input and the output and how it's the dimension here?
Right, so the input is going to be, let's say that we have additive valuations. Okay, so bidders have additive valuations over items. So if I get a water bottle and if I get a coffee cup, then the value that I'll get for that bundle is just the sum of the values I have for each of the water bottle and the coffee cup. Then for this, the input to the network is going to be for every bidder, for every item, that bidder's bid for that item. Okay. So if I have, say, 2 items and 1 bidder, my input is going to be just 2 numbers. Bidder 1's bid for item 1, bidder 1's bid for item 2. And the structure of the network is incredibly basic. It's just a stack of ReLUs, I think a couple hidden layers. It's very, very small. And then the output is going to be 2 things. An allocation vector or an allocation matrix if you have more than 1 bidder. An allocation vector for this case, which says, here's the probability that you'll get item 1, here's the probability you'll get item 2. And then a payment vector, which is going to be how much I charge each bidder. Okay, so in the 2 item 1 bidder case, it's just going to be 1 number, the payment, and then 2 numbers, the probabilities of getting item 1 or item 2.
So does the kind of the certificate, what does that mean here? So your input is the number of users times the number of items?
So the certificate here would be, this is not a global certificate, this is pointwise. So basically it's saying if you, for this specific case, as bidder 1, draw the private valuations, say 0.5 and 0.2, so 0.5 for item 1 and 0.2 for item 2, and you bid truthfully, so you input into the system 0.5 and 0.2, then what the inputs to the system, the strategic bids that would maximize your utility given that private draw and given that current RegretNet would be, in this case, it looks like something like 0.35 and 0.2. So it's going to be the strategic misreport of your private types, of the private types of the agents, that results in highest regret. Right? So in a perfect world where we don't have any regret, all of these red dots would be on top of the blue dots. But this is just showing that this underestimates regret.
Right. So the input is related to the item. So I'm wondering, because so you will give some distance in the input, which is data dependent, and then you will look at the output of the RegretNet, right? So I wonder what is the input variation mean here?
It's a strategic misreport. So I, as an agent, right, I'm going to draw a private value for the items, right? I'm going to draw 0.5 and 0.2 or whatever for my 2 items. And if I have an incentive compatible mechanism, then the agent would never be incentivized to report something other than 0.5 and 0.2. If I don't have an incentive compatible mechanism, then there exists some misreport of 0.5 and 0.2, so something else, 0.9 and 0.3, that results in higher utility for that agent. And that's what this is saying.
I see. So you're basically looking at how trustworthy the agent is here?
Well, we're not assuming that the agents are trustworthy. We're assuming that they respond to incentives. And we'll design the system such that the incentives push them toward selfishly acting truthfully.
I see. Okay, thank you.
Yeah, great questions. Cool. So some quick discussion here. So RegretNet underestimates regret. And I'm picking on RegretNet, but all these, gradient-based optimization methods will do this when you have more than 1 bidder, at least. Caveats for the Shen et al. And the RochetNet papers. We can produce bounds on the max regret that a player could suffer by being truthful, okay, under a particular valuation profile, under 0.5, 0.2. And this is nice, right? We can maintain some provable properties. Scalability is an issue, right? So our IOP embedding, like I mentioned, is pretty naive. There's a bunch of really cool work, coming out of, for example, Google. I think Ross Anderson is a lead author on some of this kind of stuff, looking at math programming, sort of, column generation and branch and price style stuff for solving these sorts of problems, or tightening the representation and things like that. Those would all speed this up. So this is a proof of concept. And a couple of quick calls to action here. One would be to incorporate this into the training procedure, right? This is if you train a RegretNet, then we tell you how bad it is in specific cases. It'd be cool to implement that into the training procedure. And two would be to actually do a global certificate as well, right? So instead of having to iterate over all these different, little blue points, so draws of valuations, I would like to have some sort of global certificate as well. And so that would be interesting future work. Cool. So in the remaining, 3 or 4 minutes, I'll kind of breeze through some of this work. I'd like to talk about some recent work we have, which is it's a fundamentally different way of training these sorts of networks, and it does allow for different demand types than for example, a RegretNet style approach can handle. Okay. And we're calling this learning revenue maximizing auctions with differentiable matching. And it fits within the differentiable programming and differentiable economics space. So one of the outputs of these RegretNet style approaches is this allocation matrix, right? For every item and for every bidder, this is the probability that I will allocate you that item. And the feasibility of that in RegretNet is enforced via a mixture of sort of soft maxes and mins. And that's a function of the demand type of the bidders, unit demand, additive, and so on. Okay. So here's a quick example. If you have unit demand, remember, I'm going to get value for the most valuable item that I get, and everything else just goes out the window. Here, bidders, another way of saying that is they want one item, and it's the one they want the most. I'm going to softmax over the rows, right? This is going to basically allow me to allocate at most 1 mass on a single item. I won't allocate 2 of one item, right? I'm going to softmax over the columns in this allocation matrix, right? Which is going to give me this one total item mass to a bidder. And then I can take a min over this, which is going to give me exactly one item. So not 0.5, 0.5. It's going to min me to only one of those. Okay. So I have a series of these soft maxes going over my allocation matrix and maybe some mins as well. And those will look different based on the demand types. Okay. The combinatorial settings, so like general combinatorial auctions where I have maybe combinatorial preferences, or I value bundles at something other than additive, is similar. But I'm going to need a larger set of inputs and a larger set of outputs. Okay, but it's similar. Cool. So our aha moment for this paper is, or this under submission paper is that a feasible allocation of items to bidders is just a bipartite matching, right? Items on one side, bidders on the other. Could be B matching if they want more than one item, or if I have more than one item, but it's matching, right? So I can formulate this if I want to as a discrete optimal transport problem, right? And if you've never heard of optimal transport, the 50,000 foot view of it is basically I want to move a set of masses to another place, and I don't want it to cost me very much. Okay. So the discrete version of this, my masses are discrete, is just minimum cost bipartite matching. Okay. So now we can use this to enforce feasibility of the allocations. Okay, so we're still going to have an allocation network. We're still going to have a payment network that looks like RegretNet, but we're going to jack on to the end of this this discrete optimal transport problem, which is going to give us a feasible allocation matrix at the end of the day. Okay. And now you're saying, hey, John, can I backprop through this? And the answer is yes. So there are a lot of ways to solve this discrete OT problem. We're going to lean on Sinkhorn's algorithm. Okay. This is great. It's been used in practice before, just not in these settings. It's iterative. It's parallelizable. It can sit on your GPU. It does all the things you would want with deep learning. And it's a method for solving a version of the min cost bipartite matching problem with an entropy regularizer to make everything sort of work well in a convex sense. Okay. So the math here isn't super important, but it's a way to solve this min cost matching problem. Okay. So on the forward pass, we'll just do what we're doing, right, with the 2 networks that we have, and then we'll hit Sinkhorn's algorithm. And the backward pass, we'll just use AutoGrad, right? So we're going to backprop through this, and everything works. Okay. So it's just a building block, a differentiable building block that we put on to the end of these networks to enforce feasibility. And we have some cool results that come out of this. Here, again, focusing on 2 items and a bidder. The evaluations here are going to be drawn independently from uniform 0, 1. And we have a couple of cases that pop up. Okay, so one on the right here is unit demand, right? I only want one of these items. Dotted line here is a known optimal auction, and this is what RegretNet or a RegretNet style approach would recover. Ours does as well, so this thing works, which is cool. On the left side is a type of demand that can't be represented by RegretNet. So we can do what's called exactly K demand. I want exactly 3 items, right? Not up to 3. I want exactly 3. And we got lucky in the sense that there's an EC 2016 paper that actually defines the optimal mechanism for the exactly one demand case. For this case, we can do multiple bidders and multiple items and so on. That isn't part of that paper. And so we're able to compare against that and actually recover it. So that's really exciting. Okay, so we see this as a nice complementary method and maybe one that's going to enable more uses for this kind of work. So I'll conclude with some thoughts, right? So differentiable economics is a new view on a classic set of problems. We want to allocate some goods to some people who want those goods, right? So this is not a new problem, it's a new approach to the problem. And there's a lot of cool work from the ML and the CLT world that can come in. There's a lot of cool work from the combinatorial optimization, math programming, operations research world that can come in here as well. Scalability, training, generalization bounds, all that kind of stuff you would worry about, along with economic stuff like preference elicitation, right? Languages I can use to elicit bids from people. A lot of exciting work here, I think, in terms of a direction, right? We can view this as a tool to push theory forward, right? I can give you heat maps, and then you can say, well, you know what, this looks like this kind of function. Maybe I can prove that's the optimal option. Kind of the pie in the sky-ist of these approaches, well, everything here is differentiable, right? We can treat this whole thing as a building block in the differentiable programming paradigm. I can throw this into like an RL setting if I want to, right? I think it's great. But we probably want to get a better grip on scalability in the single shot setting first. Cool. So I'll conclude with that. Again, I'd like to shout out to my co-authors here, especially sort of the lead PhD student on a lot of this line of work is Michael Curry, and then many folks here. And again, I'd like to point out Anthony Astuni here, who will be starting as a PhD student in your very department in a few months. So thank you.
Hey, John. Yeah, thanks so much for the presentation. It's really interesting. I'd love to hear more of your thoughts on the RL setting. Like, is in the RL setting, you will train, like, so basically you will hope to train an RL agent that will give you like the optimal strategy here, or?
Yeah, it's interesting, right? Like, it's interesting, right? So we have allocation mechanisms, and we don't do any behavioral modeling of the agents here, right? We're assuming that they're going to truthfully report their sort of types to a central system. If I wanted to do something like incorporate, I don't know, computational models of thought, or if I wanted to do like bounded rationality in my agents, or if I wanted to do something like that, or maybe collusion between my agents, right? Let's say that people talk to each other before they come to market or whatever. Then I have to sort of I'd have to wrap these sorts of approaches in a greater sort of dynamic system. So to me, that's one interesting direction forward. You could imagine having the design of an auction or the design of any. This could be used for, like, if you can backprop through it, you can use it for, like, discrete allocation of goods, matching. You could use it for. There's been some interesting work using this for like the design of voting rules. You could have those mechanisms evolve with the underlying dynamics that are evolving in like a multi-agent reinforcement learning system. So like from a like, do all the pipes fit together from a type checking point of view, this would fit into a model like that. That thing would be a scalability nightmare, right? Like, we can barely train these models right now, and we can barely train RL right now. So like putting them together, it would be a scalability issue. But from a do the pipes fit together point of view, I think it fits together, which is kind of cool.
I see. Thank you.
Can I ask you something about your notion of fairness? I know you said that it's sort of arbitrary, but so when you're going through and trying to sort of calculate your loss function, in that setting, the idea is you're excluding the protected characteristics, right, from the sort of distance function. But then on the revenue side of that equation, like, can the buyer still have a preference that includes those protected characteristics?
Yes, yeah, for sure. I mean, the bid isn't coming in with any sort of like metadata. It's just the bid is associated with like agent 12. They bid 0.6 for item 3 or whatever. And that bid, right, the private valuation that an agent has is drawn from a distribution, a public valuation distribution. And that public valuation distribution can absolutely be a function of sensitive attributes. So let's say that the sensitive attribute is name John or not name John. It could be that all Johns love item 1. And so my distribution for item 1 is going to be much higher than Rebecca, who, let's say you're name is a sensitive attribute, and all Rebecca's hate item 1, and so your distribution for item 1 is tightly coupled in 0. Let's say that's fine. Yeah. So that's input to the system, and if your sensitive attribute, or if any attribute about you, it doesn't have to be sensitive, right? If that can absolutely impact the distribution from which you draw your valuation for an item. Yeah.
Oh, no, but not the distribution from which I draw my item, right? Like, so because I'm thinking in the context when you're talking about job ads,
yeah,
right? So you're saying I can't decide who I show my job ads to based on a protected characteristic, but like the hiring firms may have discriminatory preferences.
Oh, I see. Okay, so you're saying basically, oh, I'm not sure if that would collapse into revenue, but I do see what you're saying, which is basically I count somehow the dollars that I extract from John more than I count the dollars that I extract from Rebecca. Is that what you're saying?
Yeah.
Yeah, you could do that, yeah.
Okay. Because that's gonna like mechanically leave this sort of gap in your allocation, unless there's some like visible characteristic that's correlated with your protected characteristic.
What is this here? Is it the inclusion of that coefficient in front of the revenue for Rebecca dollars, or is it?
Yeah. So if you have that, like, so if you have, I mean, if part of my revenue, for instance, is sort of this cost of showing the ad to Rebecca, who I would prefer not to hire because I don't like people named Rebecca, then that's going to show up in my revenue function, but there's sort of not going to be a way that you're directly preventing your mechanism from assigning, like reflecting that preference, right? Which may be sort of how you want to like undo this discrimination. But then if that's happening, then you never want the fair allocation to perfectly match the allocation with, like, it's a good thing to maintain some unfairness.
I'm not quite following the second part of that. So I'm not quite following the second part of that. So I think you're imbuing maybe preferences on the clearinghouse. So what I'm doing that as well, obviously, right? So I'm saying I want to do revenue maximization subject to some form of fairness. And so you're saying this won't represent that accurately. I'm not sure. I'm not sure if I.
No, I think it will represent it accurately. I guess I'm just not sure, like, then how you show what like optimality is.
I see. So the optimality here would be some form of calculated. Oh yeah, come back. Sorry, 1 second. Would be measuring something like unfairness, which would be, yeah, an optimal, yeah. So optimality here would be, okay, so what would the analytic optimal mechanism or auction be here? It would be a revenue maximizing auction subject to the following 2 constraints: incentive compatibility or dominant strategy incentive compatibility, and it would be over the space of all feasible unfair allocations. So it's just with respect to that one constraint that we need for every pair of items that are within distance d of each other. The total variation of their allocations across all bidders is less than or equal to their distance. So the analytic optimal auction would be the one. So of all the incentive compatibility auctions and of all the auctions that result in fair allocations by the definition of fair for every input, it's the one that results in the maximum revenue. So that would be the ideal, and so that would be what we would compare sort of as a like an optimal yardstick to.
Right.
Yeah.
Yeah, but then your optimal like the measure of optimal, I guess, includes something that is like definitionally sort of unfair, assuming that you allow. I mean, sorry, I'm coming at this from the econ side, not the CS side, so that I'm sort of thinking about this in the context of like customer discrimination or something like that. And so if your goal, like in designing this mechanism, is to like prevent your sort of ad customers from discriminating, then your allocation is not going to match that like revenue maximizing optimum. And then I'm just wondering sort of how you like then you don't want those graphs to end up looking the same, I guess. And I just wasn't sure if you had a way of measuring that.
I think the answer to this is no. Again, I'm not sure if I exactly am following you here, but I think the answer to this is no right now. The yardstick against which we compare ourselves is literally just the revenue maximizing subject to those two constraints. So, so if you're saying that what pops out of that is not fair by the definition that you're defining, that may be the case. But I think I'm not following exactly what that definition is.
Okay.
It's like a different outcome. Like you're saying, like an outcome, like if I were to run this. Oh, if I were to run this, we would have.
Like if I'm more willing to pay for job ads that appear in front of men,
right,
then that's going to show up in revenue, but
right.
That's like discriminatory, and so you.
I see. Oh, I see. Yeah. This would not prevent that by any means. Yeah. Like so. Okay. So let's go back to the John Rebecca example where John really likes item one. So let's say that John is discriminatory and only wants to advertise to men. So my valuation for men is just really high, and my valuation for not men is really low. This would be reflected that. Yeah, that would be unfair. Yeah, definitely. Yeah, I agree with you.
Okay. Yeah, and it would be interesting to sort of see like if you can separate like which of the costs is coming from like the sort of consumer preferences versus the algorithmic discrimination, I guess.
Yes, I totally agree. That's actually a very good point. I would love to follow up on that actually. Now that we're finally on the same page. I agree that would not do that. That would be an issue. Yeah.
Yeah. Sorry, I'm like coming at this from a little bit of a different but yeah, so just because in terms of the discrimination stuff, you kind of you want to figure out like what is coming from feedback and what is sort of a structural issue, I guess.
Yeah. This would not solve that.
Yeah. All right. Well, thank you so much for bearing with me through that.
Cool. So other questions? I think my host is just not here. So I think I might have to shut this off on my own. Other questions? Thank you all for coming, by the way. Cool. Well, Rebecca, I would love to follow up with you. So maybe I will shoot you an email after this. And thank you, everyone else. I will. Yeah,
that sounds great. You can. I'm in the, or I'll email you because I'm sort of hard to find in the HTSI environment, okay. Just so you know who I am. Awesome. But yeah, it was nice to meet you.
All right. See you, folks.